Hello. In this video, we're going to look at double integrals over general regions. To get us started, let's take a look at a picture, right? So suppose we had a surface, and we'll just say our surface looks a general looking surface like that. And so we have z equals f of xy. And then beneath our surface, let's say that we have a shape. Let's say that our shape looks something like this. All right, where the top of our shape is defined by y equals h of x, and the bottom of our shape is defined by y equals g of x. Okay, and then so this is our shape that's directly beneath, and then we take that shape and we just extend it up until it hits the surface, and that's going to create a volume, right? So if we do that, what's that going to look like, right? So we'll start by going up here at the intersection at this end, and then we'll go up here at the intersection at this end, and then we'll go through and say that maybe the right side of our shape looks something like that, and then the left side maybe looks something like that. And so that's our three-dimensional object. Okay, so what we want to do is to be able to go through and add up the volume under the surface and above this shape. So it's the same topic as the previous section, except in the previous section we went over rectangular regions, right, where there was a rectangle directly beneath the surface. So now we're finding the volume below the surface and above a general shape. Okay, so in order to go through and do that, right, what we need to do is we need to go back and actually do some review from previous course. So what we want to do is we want to go back and recall how to find the area between curves. Okay, so there were two types of area between curves problems. So one type looked like this, right? So we'd have a top, and we'd have a bottom, right? And the top, I'm going to intentionally use the same type of function that I had over here. And so I'm not going to use f. So our top is going to be, let's say our top is y equals h of x. Our bottom was y equals g of x. And if we wanted to go through and find the area between the curves, what we ended up doing is we ended up finding the integral of h of x minus g of x dx, and then where they intersect, we'd have a and b, and so we would do that from a to b. So effectively, what we ended up doing is we ended up finding, using a vertical rectangle, right? So there's two ways you could think of this. You could either think of this as you integrate from the top all the way down to the x-axis, and you integrate from the bottom to the x-axis, and then you subtract the two. Or you could think that you have a strip that just goes from the top to the bottom, and then you're just adding up between the two that way. So they're both the same. You get the same result. But we ended up using vertical strips like this to go through and add up the area. The problem if you try and use horizontal strips is that you run into, you run into a bunch of issues actually. So what we need to do is we need to use these two functions. If you go through and you try and use a horizontal strip, like if you try to do something like this, and move that up and down to add up the area, then you end up having, you have a different function on the right for part of it, right? So you'd have a different function on the left side. Here you'd have a different function. Well, I guess it's the same function, but you'd have to go through and have find some place to split those up where you'd have the left side is defined by a function and then the right side is defined by a different function. And they're going to switch functions here at this point, and they're going to switch functions here at this point, like the right and left. And so it just becomes a really difficult endeavor to go through and try and do left to right. And so when you have functions that are shaped this way, where you have a function that just makes up the entire top and one function that makes up the entire bottom, then the easiest way to go through and find the area is to do top to bottom. Okay. And so the same thing applies, or I guess the equivalent thing. Oh, whoops, erase the bottom of our shape. The same idea applies if you have a consistent left and a consistent right? So if we have functions that look like this, right? So where we have a function that looks like that, and then a function that looks like that, where we have the right side is defined by x equals h of y, and the left side is defined by x equals g of y, then in that case, we would go through and integrate, right? We could go through and say C and D is where they intersect. We could integrate from C to D, and we would do h of y minus g of y dy. Okay, so in that case, we would end up using rectangles that went from the left to the right. Okay, and so we ended up with these two situations. If you've got functions of x and a clear top and a clear bottom, then you did from top to bottom. And if you had functions of y, then you'd have a clear right and a clear left, and then you did a strip that went from left to right. All right, so for the context of this class, what we're going to do is we're going to call this first one, we're going to say this is a type 1 area between curves problem. And then we're going to say this is a type 2 area between curves problem. And so if we transition back to our volume problem, you can see that the way that I've drawn the base and the way that I've described it with functions where you have y equals a function of x and y equals a function of x, this is a type 1 base. So we have a type 1 base. All right, if we were going to go through and find the volume that's underneath this surface, what it's going to require that we do is it's going to require that we end up moving a rectangular box, just like from the last section with the rectangles. It's going to require us moving a rectangular box around this region to go through and add up the volume. So what I mean by that is that if I went through and took and drew a little rectangular box in here, hopefully I'll do my best. Not bad. If I took a rectangular box, right, then to add up the volume, I'm going to use this box. And the way that I'm going to use it is I'm going to move it around inside of this base, just covering all of the region, okay? And just at a given instance, I just take it, find the volume there, move it, find the volume in another spot and add it, find the volume in another spot. And so what we're going to do is we're just going to add up a bunch of rectangular boxes to go through and add up the volume that's inside here. And so if we're doing that, then what we can do is we can just focus on the base, right? And ignore the vertical part of this. The vertical part is always just going to be taking points and plugging it into the function. So we can focus on the base and actually focus on taking the little box I have here in the base and moving that around instead. And so that way it just simplifies the problem and makes it easier for us to wrap our minds around it. So let me be more explicit, right? So what we can do is we could go through, and instead of thinking about the whole three-dimensional problem here, if our goal is just to take this rectangular box and move it around to add up the volume, then what we can do instead is look at, right, say this is h of x, right? That's this curve is the same as this curve. And then this is g of x. And then this little square here that's at the bottom, which doesn't need to be perfectly square, on this picture, it looks like that. Okay, that's the equivalent. And so what we've done is essentially it's like we're looking straight down on the object. And by looking straight down on the object, it like can simplify the problem. And so the problem becomes, how do we take a little rectangular box like this and move it around to end up covering this whole region? All right. And at each point, there is going to be a vertical component. There is going to be a height. It's just that we can't see it. And what we're going to end up doing is just taking the point and plugging it into the function to get that value. And so it's not a particularly interesting or difficult part of the problem. It's not a challenging part. The problem becomes, how do we take this and move it around to cover this this region, this two-dimensional region? So to figure that out, let's zoom in. All right, so what we've got is we've got a function that's the top. This is h. And we've got a function that makes up the bottom. This is g. And what we need to do is we need to find a way to cover this region in an organized fashion with these little boxes. Okay. And if you go back to the last video, we did the same thing with a rectangle. It's just with a rectangle, it's very simple. It's a very simple, there's a very simple way to do it, but it's much more complicated to go through and handle an object that has a general shape that's not a rectangular shape. So how can we do that? Well, what we can do is we can go through and just recall what we just went over, right? So when we're finding the area between curves, what we found was the easiest way to do it was to take, was to go from top to bottom, right? To have a rectangle type shape, and then, oh shoot, I was trying to erase that little bit in the middle. Good try, didn't work. What we could do is we could go from, we found that it was easiest to go from top to bottom. If we tried to go left to right, we ran into all kinds of issues with figuring out what the left function was and the right function, you know, transitions between functions, all this other stuff. And so since the shape that we're dealing with for the base is type 1, this type 1 result that we got from Calc 2, I think, is something that we can go through and use to try and figure this out. So what that's telling us is that's telling us that vertical strips would be the easiest way to go through and do this, right? So we could go through and we could draw a, you know, box like this, and then a box directly above it, and then a box directly above that, and then a box directly above that, and then a box directly above that. And we would end up getting, you know, again, so keep in mind that what we're doing is we're just showing the part of the base. What you'd be doing is each one of those squares represents a rectangular box that's going from the bottom of the object all the way to the top, the base of the object all the way to the surface that's directly above. So there's directly above this, there's a rectangle that's coming up. Directly above this is a rectangular box that's coming up, and so on. So this gives us a strip of volume for the surface that if we were to draw it on, this would look something like that, like that, like that, and so on. Okay, and then above each one of these, there's a vertical component, which I'm not going to try and draw because it'll just make the picture into a mess. Okay, so this type of organization where we go from bottom to top is something that we could go through and use as a default idea for how to do this coming from our Calc 1 results. So now the particulars of doing this are actually kind of interesting. And so I do want to spend a few minutes talking about them before we just assume that this works and that great idea, we'll just inherit what we did from Calc 1. All right, so suppose we have A and we have B. So we have the left and the right side, right? So let's just go through and just actually see how this would end up working in actual practice if we tried it, right? So the way that we handled in the last section, breaking this up, is that we started with A, you step over, you get X1, right? So that's going to be your first X value is 1 step over. And then if you stepped over again, you'd get X2, and you'd step over again, you'd get X3, and you just keep taking these steps. And that's how we break up the object, okay? So if we're at X1, right, how can we go through and figure out where to put our boxes? Okay, how can we figure out where to draw them? Well, what you could do is you could take X1 and you could plug it into these two functions, right? If you take X1 and plug it in, it's going to give you this point. This is going to be, right, that's going to be g of X1. And then if you take that point and plug it into h, you're going to get h of X1. So by taking X1 and plugging it in, it enables us to figure out where the top and bottom of our object would be. And then from there, we could just go through and break that interval up and put boxes there. So we could put a box, and then directly above that, we could put another box. So now we've added up the volume that's along that strip between A and X1, right? And then if we went to X2, we could take X2 and plug it in, and it would give us g of X2. And plug it into h, and you'd get h of X2. And so we would then end up getting our vertical strip, and then we could go through, or get the top and bottom of the object, and then we could go through and put boxes. And we ended up going a little bit over, but that's all right. All right, and so that just in practice, right, that's what we could go through and do. And that's why the vertical strips work really well, is because if you start with X, you can take X, plug it into these two functions, and they'll tell you where the top and bottom is. If you try and go left to right with the boxes instead, then you run into the same problems that we ran into when we discussed going left to right in our type 1 picture, right? And that is that if you were to go through and say, you know what, I'm going to start here at, y, whatever, we'll call it yi, then what are you going to plug it into to end up getting this point and this point, right? We have functions of X. We don't have functions of Y. So you'd have to go through and take these and convert them. And then if you did that, you'd have to solve for what the function is that's here on the left side. You'd have to solve for what the function is here on the right side. You have this little kink that would become a problem. So there's just a ton of issues if you try and go through and do this using the type 2. And so it's important with these problems to be able to, to recognize that and identify, which type of object you have for the base, and then that will shape how you actually go through and do the problem. Okay, so hopefully that makes sense, right? So if you've got a base that's shaped by a clear top function and a clear bottom function, then we should go bottom to top. And so to use the terms that I used in the last section, what we're doing is we're using vertical strips, right? So you could think about it if you want to, that we're integrating this way, or we're going to integrate this way. We're going to add up using vertical strips. Okay, so to take this and turn it actually, from just a basic idea, a basic problem that we want to solve, to turn it into actual integrals, what we need to do is apply our ideas from, the same ideas that we used in the last video to go through and transition, right? So we start off, we have the limit as m and n go to infinity. We have a double integral, I equals 1 to n. We have a double integral, j equals 1 to m. We have f of x sub I j, sub x sub I y sub j, and then we have changing a. So this is what we came up with as our general formula for going through and evaluating double integrals in the last section. So we need to go through and actually break this down into our specific case before we can go through a series of steps and actually end up at an integral. All right, so in terms of the first thing that we could break up, the change in A. So the order of integration is something that we actually do have here. So the order that you're using is that what we're doing is we're setting x first, right? So when I went through and I explained this, I said we have x1 and then we take x1 and we plug it into our function to find the bottom and top. So we're setting the x value and then doing a strip across the y. Set x, strip, or increment x, strip. If you're doing strips that go in the y direction, then that means that the order of integration is going to be inside of here. We're going to do y then x. Okay, so the order of integration goes inside out. It goes the direction of the strips first, and then the direction of the thing that you're incrementing second. So what we can do is we can break this up into limit n to infinity. So n is the one that goes with x, and then limit m to infinity. So that's the one that goes with y. And then we're going to have summation, and we'll have the x be the outer one, and we're going to have the y be the inner one. And then we'll have f, I forgot my little stars here, f of x sub I star, y sub j star, and then this is going to be change in y, change in x. Okay, so now if you look at this and compare it to what we just described, right? So what happens? You set the outer value, so the I equals 1 to n, that occurs first, right? If you were just doing this problem, you're thinking from left to right, that happens first. So what that does is that sets the x value. So that's going to say I is 1, then I is 2. So that's going to set us at x1, then x2, then x3. So that's the outer. And then the inner summation here is taking j and taking it from 1 all the way to m. So that's going to be 1 to m. So you're going to do x1, and then j is going to go from 1 to m. Then you're going to do x2, and then j is going to go from 1 to m. And then x3, and then j will go from 1 to m. And so you're adding up in these vertical strips, and the j going from 1 to m, j incrementing, the y coordinate incrementing is what causes the vertical strip to happen, right? And then the I increasing ends up causing us to go from left to right after we finish each vertical strip. Okay, so now it's not critically important, but I think it's interesting to go through and actually figure out what are the change in y, what's the change in x, what's the coordinates for x sub I and y sub j, and we're going to use this picture to figure all those out. All right, so if we're doing x first, we can go through and we could say x sub I equals a, right, plus I times change in x. That's the normal formula that you use for using the right side for the heights from, if you think about it in terms of Calc 1. All right, and then we have change in x. That's going to be b minus a. That's the interval, the whole interval, over n. So that's just the default stuff. There's nothing complex about that. But where it gets cool, or where it gets interesting, is going through and defining y sub j. So what did we do for y sub j? What we did is, when we plugged in x1, we started at g of that x value and went to h of that x value. All right, so if you think about it, it's going to be g of x sub I plus j times change in y, where change in y is equal to h of x sub I minus g of x sub I all over m. All right, so what does that say? Oops. What does that say? It says we start at g of x sub I. We start, we take the x value that's our location on the x-axis. We plug it into the function g. That gives us this point here. Then we go through and figure out, well, how far are we going to go? Like, we're going to go from h to g. We're going to go from g all the way to h. And so to figure that out, you're going to take the difference between those. We're going to go from top all the way to bottom. So you've got to subtract those two to get the full range of values, right? So the equivalent of b and a, right? So the range of values for x, we're going from left all the way to right. The range of values for y, we're going to go from bottom to top, but that bottom and top changes throughout. And so we need to use our g function and h function to figure out what the distance is, and it's going to be different every time. So just like we did b minus a here to go left to right, we're going to do h minus g to do top to bottom. And in particular, we're going to do it at x sub I. Okay, anyway, that's a lot of detail. I think that stuff is cool, but you may be rolling your eyes. All right, so let's go ahead and move on, right? So once we've gone through and set it up this way, you can do limit n to infinity. And then this limit for m does not affect the first summation, so you can move it inside. And we get the limit as m goes to infinity of the summation j equals 1 to m of f of x sub I star y sub j star change in y, change in x. What we can do here is we can throw parentheses around this inner stuff. So effectively, that's like we're factoring out the change in x. Since you're doing an infinite summation here, you can just pull out the change in x from all of those and just move it outside here, right? And so now for this inner integral, right, if we think about what's happening, sorry, this inner integral, it's not integral yet. If we think about this inner summation, right, for that inner summation, you're setting the I value, and then you're doing this. So you're saying I is 1, do this whole thing. Then I is 2, do this whole thing. Then I is 3, do this whole thing. So as you're doing this inner thing, each time the x sub I is not changing. It's constant. It's going to be x1 for a whole strip. Then it's going to be x2 for a whole strip. Then x3 for a whole strip. And so x sub I is constant inside of this. So effectively, what we could do is we could go through and replace this function that has two components. We could say, you know what, if x is a constant, then this is essentially like going through and doing the following instead. We could do, instead of f of x sub I y sub j, we really just have a function where only one thing is varying. It's just y sub j. And now at this point right here, if you look at that, that's our Calc 1 definition for an integral. And so we can replace that inner piece with an integral. And so we get the integral, all right, of h of y dy, change in x. And now what would the bounds of this inner integral be? Well, the way that the Calc 1 definition works is that the bounds go from bottom, the bounds go from the bottom to the top object, or from the left to the right. So it goes over the range in which you're doing values. Well, what is the range? It's defined by the values that are here in your change in x and change in y calculation. So if we were doing the integral for x, it would be from a to b. If we do the integral for y, it's from g of xi to h of xi. So we should have g of x sub I and then h of x sub I. I just think that's really cool that you end up with x sub I values inside of here. And then if you take your h of y that we went from f to h, if you go back to f now, what would that look like? Well, the y is still the y sub j we've turned into y, so that stays that way, but the constant x sub I is still going to be there. So we should have f of x sub I comma y dy change in x and g of x sub I. Hold on, let's move this over here, g of x sub I, and then here we'll have h of x sub I. And now if you think about this whole top, think about what we've got now, right? This whole inner piece here, that's it. You go through, you evaluate that integral. That integral, you're going to get a different outcome for every single x sub I, right? You're going to plug in an x sub I. So x sub I is 1. You're going to plug in 1 here. Then you could go through and evaluate this integral, get an answer. Then you could go through and you could plug in 1.1, do this integral, get an answer. Plug in 1.2, plug it in, get an answer. And so what we have here is this inner piece is just a very complicated looking function that produces an output for each x sub I. And so what we can do is, just like we went from f of x sub I y sub j to this h function, we could go through and effectively do the exact same thing. So I'm kind of out of space. I'm going to move to the next page. So you could rewrite this instead of using h, I'll use, I don't know, p. So we're going to have p of x sub I change in x. So this whole inner piece I went through and replaced with p. Oh, I probably shouldn't have used h here. I probably should have used p here as well. I apologize, because now you got h in 2 different spots. This is a different, let's just, hey, this is really easy to fix. And it's going to bug me if I don't fix it. So let's just use p here. That was p. And then this time we'll use q instead of p. Little changes on the fly. It's a thing you don't notice when you make out your notes. Right? And so now we're taking this whole inner thing. Let's do this. This whole inner thing, and we're saying this is just a very, very complicated function of x sub I. All right, and so if it's a big complicated function of x sub I, that means we could replace it with a simpler thing, a simpler representation. And then at this point, we have our Calc 1 integral formula. So this is the integral a to b q of x dx. Where does the a and b come from? It's what we just discussed. When we do the integral for x, it's going to go from a to b. So the bounds of your integral come from inside your formula for where change in for change in x and change in y. All right, so you go ahead and we can replace this with our Calc 1 integral, and then we just pop in our what we substituted. So we substituted q for this complicated inner piece. So now let's just put that complicated inner piece back in. And we get this result. And that, all of that work was all just to derive the formula, right? So this is the formula for going through and finding a volume beneath the surface f of xy for a type 1 base defined by y equals g of x to y equals h of x. Okay, so that's just one type of double integral that you could have. Of course, we talked about type 2 as well. So there's our type 1 result. You could have a similar result for type 2. I'll try and go through it quickly, but just to show you a quick little picture. So this would be the type 2 case. You have a surface. we have a type 2 base. So a type 2 base is going to look like the following. Where this would be h of y, right? So it's x equals h of y. And then the bottom function is x, the bottom. This is the bottom. Technically, everything is kind of twisted around, right? So this is going to end up being the right function if you redraw it into 2 dimensions, and this is going to be the left. I'll show you that in a minute. Right, so we've got that's our boundaries, and we could go through and end up drawing the object. So the object is going to go up, hit the surface, up, hit the surface, and then this piece would be defined like that, and then this piece would be defined like that. So that's our volume beneath the surface, z equals f of xy, where we have the base here. All right, now if you took this and were to draw it in 2 dimensions, what does it look like? All right, so this piece here, x equals h of y, becomes the right side. And then this piece becomes the left side. That's a terrible picture. That's not a very good picture. Let's try that again. All right, so it kind of goes out a little bit more like that, and then the jog like that. Yeah, it's a little bit better. Anyway, so this is x equals g of y. How can you tell, or how can I tell by looking at this, right? So here, if you think about this line is the y-axis. So this piece here should be close to the y-axis. This piece here, closer to the y-axis. This piece here, further from the y-axis. This piece here, further from the y-axis. Okay? And so, that's the situation. And now I'm not going to go through the whole derivation and explain all these details again. But what you can do is just take this and just flip everything around, and you'll get the volume beneath the type 2 surface. Or sorry, volume for a type 2 base. So it's going to be the double integral. We're going to go from g of y to h of y. And we're going to go from C to D. We're going to use C and D. So C and D in this case, this is C. This is the bottom where the 2 intersect at the bottom, at the top. So on this picture, here would be C, here would be D, and then you do f of xy. That doesn't change. And then in this case, now we're doing dx, dy. We're doing the opposite order of integration. Okay, so later on in the section, when we actually go through and do problems, all of this stuff is going to come back. So the reason I'm going into all this depth is because a lot of these ideas are going to become necessary. Your understanding is going to become necessary to actually do the problems. You're going to need to understand, why am I using type 1? Why am I using type 2? What are the circumstances that are around those? All this is all relevant. It all does kind of come back and tie everything together. However, that's later in the section. First, what we're going to do is we're just going to practice evaluating some double integrals, assuming that you just were given them, but they're over general regions. All right, so these are just some given double integrals. So they just give it to you and they say evaluate. So for these problems, it's really just about practicing doing a double integral. All the type 1, type 2 stuff is not really relevant for these problems. All right, so for this problem, they've given us, here's the function, f of xy. Here's the order of integration. Here are the bounds. The way that you can tell this is a general region instead of a rectangular region, right, from the last video, is the fact that you've got a function that's in the bounds. If you have a function in the bounds, then that tells you that you have an integral over a general region. All right, so to go through and evaluate this, we want to integrate with respect to y first. When we integrate with respect to y, what do? We treat x as a constant. So here we're going to get y cubed over 3. Leave the 2 and the x, which are constants. Leave those two alone. Evaluate it from 0 to x squared. And then we're going to end up 0 to 2. Plug in x squared. We get 2x times x to the 6th over 3. Right, so you put an x squared where the y is. So you're going to get x squared to the 3rd. That's x to the 6th. And then plug in 0, and you get 0. From there, we could go through and simplify. So we have 2x times x to the 6th. So we're going to get 2/3 x to the 7th. And then we can go through and find the antiderivative of that. So that's going to be 2x to the 8th over 3. Whatever I just said. It's going to be, well, let's just do this. It's going to be 2x to the 8th over 24. And then we can simplify this into x to the 8th over 12, 0 to 2. And so x to the 8th, you go through and figure that out. That's going to be 256. All right. And you can check that. 2 times 2, 4, times 2, 8, times 2, 16, 32, 64, 128, 256, all over 12. And then we can reduce that. So that's going to reduce to 64/3. And so there's our first example, right? Just evaluating a double integral over a general region. So one of the things that's going to come up later on in the section is going through and actually, I'm going to create this in a separate video because this section is so long, but it's going through and changing the order of integration. And so one thing that's good practice, even on these early problems, is to figure out what the base of the object looked like. Okay, so what was the base, right? So, in terms of all the stuff that we just finished talking about, can we go through and pull it out? All right, so if we have dy dx, let's just look back. When we have dy dx, that's our first formula here. What did that say? That said that we had function of x to function of x, right? And what did we know about those functions? Those functions represented the top and the bottom of our object, right? So we went from g of x for the bottom to h of x for the top. G of x, bottom, h of x, top. So here, this is the g of x, that's the bottom. This is the h of x, top. So we could go through. Now, you don't have to do any of this to evaluate the problem, but this is going to become important down the line to have the capability of doing this, right? So g of x is the bottom. So it's saying the bottom is at y equals x. Or sorry, y equals 0. I don't know why I said y equals x. The bottom is at y equals 0. What is y equals 0? That is the x-axis, right? So here's the bottom of the object. Now, what is the top of the object? The top of the object is given by y equals x squared. Okay, so we have y equals x squared. So that looks something like this. So we're told that is the top of the object. I guess I should have drawn that in red. Let's just color over it in red. Okay, and so that's the bottom, that's the top. Now, over how do you figure out, where to start and stop counting? Well, if you go back, where did we start and stop? A, B. Where did those end up in the integral? A, B. So what we want to do is we want to go use those to figure out our where to start and stop. So x equals 0 to x equals 2 is where we start and stop. So we want to start at x equals 0 and stop at x equals 2. And so this ends up being the base of our object that we ended up integrating across. Okay, so again, that's not necessary to go through and evaluate. If they ask you to evaluate, you can just go through and do these steps, and then you get to 64/3, and then you're done. But just down the line, we're going to need to be able to do this, so it's good practice to go ahead and be able to figure out what the base of the object was by pulling out the using the bounds of integration and pulling them out into a separate separate description. All right, let's try another one. So again, same instructions. They just want us to evaluate. All right, so here's the integral that they give us. So the order of integration goes dx, then dy. That means that the bounds here, our first set of bounds are x bounds. Then the outer bounds are y bounds. Okay, so to go through and integrate this, when we're integrating with respect to x, we treat y as a constant. So this cosine y is just a constant. So the antiderivative of e to the x is just e to the x. And the cosine y just kind of goes along for the ride. And then we have 0 to sine y dy. You could plug that in. Sine y gets plugged in for x, and we get e to the sine y cosine y. Right? And then when you plug in 0, right? So if we're plugging in for x here, actually, let's just change the order around to make this a little simpler. Right, so here, we'll put the cosine y on the right, on the left, and then so you plug it in for x, you get e to the sine y, and then you plug it in 0 for x, so that e to the 0 is 1. So don't forget your 1 there. All right. And then from here, we want to go through and evaluate. This is just a Calc 1 style integral. To do that, you can go through and split this up. This is cosine y e to the sine y minus the integral from 0 to pi over 2 of cosine y dy. All right, so for this piece, this is a fairly simple use substitution, and simple enough that because I have limited space, I'm just going to go through and just plug it in, right? So if you do u equals sine y, you're going to have du equals cosine y, right? And so this is going to become the integral. We're going to have e to the u du, and then y is 0. So if you plug y equals 0 in, then u becomes 0. And when y is pi over 2, if you take that and plug that in, you're going to get sine of pi over 2, which is 1. All right. And then for this second integral, we can just go ahead and evaluate this. So the antiderivative of cosine is sine from 0 to pi over 2. And then our antiderivative of e to the u is e to the u, 0 to 1. And then minus, so sine of pi over 2 is 1. Sine of 0 is 0. So this is going to be minus 1. And now if we plug these in, we're going to get e to the 1 minus e to the 0 minus 1. So this is going to become e minus 2 would be our answer. Okay. So now the other thing, the thing that we did on the last problem, I wanted to go through and do again on this problem, and that's, whoops, that's taking our base, the base that we're integrating across and identifying it using the bounds. Okay, so we want to go through and do that again. So how do we do that? Well, so this is a type 2 integral. It's important to recognize the type. The type is based upon the order of integration, right? So how did I recognize this was type 1? Because of the dy dx, right? If you go back, to our formulas. Here's type 1 has dy dx. Type 2, dx dy. So that's how I recognized with this problem that I needed to, that this went bottom to top, then left to right. So for this problem, it's type 2. So this is going to go left to right and then bottom to top. So if we go through and draw coordinate axis. So this is going to be the left side. The left side. So what's x equals 0? That's the y-axis. So this is the left side of our object. And then what's the right side of our object? The right side of our object is defined by sine of y, right? So what does x equals sine of y look like? Well, so it looks like y equals sine x, but reflected across the line y equals x, right? So we know what y equals sine x looks like. So let's just kind of sketch part of that just to kind of get us the idea, right? So here's y equals sine x, right? But what we want to draw is we want to draw x equals sine y. So to go through and do that, what you want to do is you want to take this picture and you just want to reflect it across the line y equals x. Or another way of saying that is what we're doing from left to right, instead you want to do from bottom to top. So what would that look like? So you have this hump here that's directly above the x-axis. So if you were going to reflect this, you're going to have that same hump, but it's going to be directly to the right of the y-axis, right? So instead of being above, it's going to be to the right. That's the idea. So it's going to look something like this. And then we can go through and erase that. So that's our x equals sine y. Here's x equals 0. So that's that's part of our object. And then how much of that object do we want? That's what the outer set of bounds tell us. They say we want to go from 0 to pi over 2. All right, so we want to start it here at 0, and we want to stop at pi over 2. And so this piece here, that is going to be the base of our object, right? So from 0 on the left, that's the y-axis, sine y on the right, that's this curve x equals sine y, and then do that from y equals 0 for the bottom to x equals pi over 2 at the top. Okay, so that's the idea. It's just same idea as we did here. So bottom, y equals 0, top, y equals x squared, left, 0, right, 2. Okay, left, 0, right, sine y, bottom, 0, top, pi over 2. So that's how you can go through and create the base of the object by using the bounds, is that process that we just went through. Okay. Let's go through and do another one. Or no, hold on. Nope. My apologies. The next thing that we're going to look at is we're going to move on. I thought I had one more example, but I don't. We're going to move on, and we're going to look at actually going through and, given a problem, how do you pick the order of integration? So if we're not given the order, how do we pick it? All right, so what I mean by that, before I go into the description, so suppose you were given this problem, but this had dA here, and they had put an R here, and then they described the R off to the side. How would we go through and do it? How do you pick the order of integration? All right, so step 1, what you're going to do is you're going to draw the base / region of integration. So step 2, You're going to look at what you just drew, and you're going to determine, is it type 2 or type 1? And then sometimes it could be both, right? If it's both, what you're going to have to do is you're actually going to have to look at the function and identify which order of integration would be easier. So sometimes it can be both. Once you've done that, next thing you're going to do is you're going to go through and set up the integral. If type 1, then the order of integration is dy dx. If type 2, then the order of integration is dx dy. Right? If it's type 1, then the top and bottom functions are going to be the inner integral. Right? So type 1 goes bottom to top first. If it's type 2, you have left and right. I guess we should be consistent here. If I use top first, top is equivalent to right. So you have right slash left functions are the inner integral. All right, and then the last step is to actually evaluate. All right, so let's see if we can go through and follow those instructions. These problems do get to be a little bit complicated. And if you're taking a multivariable calculus class and watching these videos, like my students are, then this is probably the hardest thing that we've done all semester. All right, so suppose you have this problem you want to evaluate. They use D instead of R for some reason when you have a general region. I don't really know where the origin of that comes from. Okay, so they want you to go through and evaluate. You're asked to evaluate this this double integral, and here's the function. So just to keep tying this all back to the beginning of the lecture. So this is the top of the object, right? So what I mean by top of the, you can get top and bottom can kind of get all screwy in these sections. So top meaning this, it's the surface. So you've got the surface, is defined in this problem by just x. So here's the surface, and then here's the object that's beneath the surface that we're using to identify where to count, where to add up volume. Okay, so what do we do first? Draw the region of integration. Draw the base. We want to draw this. Draw this. Okay, so what are we drawing? So we've got y equals x squared, so that's a parabola. Now I'm not going to bother to draw the left-hand side because we also have x is greater than or equal to 0. And then we have y equals 2 minus x squared, so that's a parabola that's opening downward. All right, so here's x squared. Here's 2 minus x squared. And then x greater than or equal to 0, so that not only does that tell us that we don't need the left-hand side, but it also gives us a bound for the left, and that is the y-axis itself. The y-axis is at x equals 0. All right. So what we've got here, if you look at that picture, is that type 1 or type 2? One of the giveaways when it comes to type 1 and type 2 are the way that the functions are described. So if you're not sure just by looking at the object, so ideally you could tell just by looking at the object, type 1 objects have a single function for the top and a single function for the bottom. Type 2 objects have a single function for the right and a single function for the left. Sometimes those ideas can be a little confusing to students. And so the other thing that I usually tell people is that the functions themselves can be a big, big hint as far as type 1 or type 2. So if you go back all the way to the beginning again, right? So notice that the type 1 has y as a function of x, y as a function of x. If you're given functions that are in terms of x, we have y by itself, and then you have a bunch of x stuff, y by itself, and then a bunch of x stuff, that's typically going to be a type 1 shape, right? Meanwhile, look at the type 2 that we did, right? We had functions of y where x was by itself, functions of y where x was by itself. So that can be a big hint as far as whether you have a type 1 or a type 2 object, right? In this case, we have functions of x, and we have a single function defines the top and a single function defines the bottom. So this is a type 1 object. What I like to do when once I've drawn my picture is to go ahead and just put a rectangle in there, showing like that's the way that our strips are going to work. Now, we're not actually using the whole rectangle here. We're breaking it up into pieces, right? So we're doing a strip that goes from top to bottom, but it does kind of give us the basic idea that the way that we're adding up volume is we're going this way. We're doing vertical strips. So vertical strips is type 1. And so now that we've got all that, we can go through and set up our integral, right? So draw the region, determine whether it's type 1 or type 2. That's what we were just doing. So we've already done that step. Step 3, set up the integral. If it's type 1, you put dy dx. So we want a double integral, x, dy dx. All right. And then as far as the inner values, right? So what is it? What did we write down? If type 1, the top and bottom functions are the inner integral. All right, so the inner integral, the bounds for the inner integral are going to be y equals the bottom. So it goes bottom to top. So we've got bottom. Bottom is y equals x squared. Top is y equals 2 minus x squared. And then we need to go from x equals 0. That's the left-hand side. I didn't write that down because I kind of ran out of space. But the left and right are the outer bounds for type 1. And then here, we need to know what this point is to figure out what our top bound is. How could we find that? Well, we have a function here that's x squared. We have a function here that's 2 minus x squared. We want to know where they intersect. To figure out where functions intersect, you set them equal. So if you do x squared equals 2 minus x squared, then you're going to get 2x squared equals 2. Then x squared equals 1. And so they intersect at plus or minus 1. right? So plus or minus 1. We don't care about the negative 1 that's over here. 1 is the one that we care about. All right, and so once you have the integral set up, then we can go through and evaluate the integral. All right, so to evaluate the integral, we're going to integrate with respect to y first. So x is treated as a constant, so don't do anything with it. And then we get y, so we're going to have from x squared to 2 minus x squared. Then plug in for y. So we're going to have x times 2 minus x squared dx. So we're going to have the integral 0 to 1. We get x 2 minus 2x squared dx. Calc 1 style integral here to go through and do our Calc 1 integral. You could just distribute this. This is 2x minus 2x cubed dx. The antiderivative, so we're going to get x squared minus 1/2 x to the 4th, 0 to 1. So we get 1 minus 1/2. Plug in 0, you get 0. So this is all turns into just 1/2 as our result. Okay. So there's an example. If you were given an integral to evaluate where they gave you the region, but they didn't tell you what the order of integration was, so you had to pick. All right, let's try another one like that. All right, so suppose we had the double integral over d. We have y squared e to the xy dA. And let's say d is bounded by y equals x, y equals 4, and x equals 0. All right, so what do we do first? Step 1, draw the base. We need to know what the base looks like in order to figure out whether it's type 1 or type 2. So we can go through and draw the base. What do we have? So it's bounded by y equals x. So y equals x. And then y equals 4. So y equals 4 is a horizontal line here at 4. And then x equals 0. That gives us the y-axis. All right, so that's x equals 0. All right, so here's our region that we want to integrate across. Okay, and this is a good example of an object that's both type 1 and type 2, right? So what does it mean to be type 1? It means that you have a single function as the top and a single function as the bottom. So it means I could go through and draw a rectangle that looked like this. Touches the bottom, touches the top, and does so across the entire object from left to right. Well, but hold on. So couldn't we also go through and do the same thing and draw a rectangle that looks like this, and then that touches the left side and the right side for the whole object? And so it's both type 1 and type 2. Yes, it is both. So this is both type 1 and type 2. That is going to happen when you go and do these problems. And then suddenly you're going to have a choice to make. So that's actually a good thing because it enables to have choice in terms of how to integrate. But it's a bad thing in that choice makes the problem a little more complicated. All right, so what did we say in our instructions here? If both, look at the function to determine the easier order of integration. So where is the function? This is the function. This is f of xy. All right, what would be the easier order of integration to do here? All right, well, if you think about it, if you just look at it, if you had a choice, would you rather integrate with respect to x first or with respect to y first? If you integrated with respect to x first, there's only one x, right? So that would make things simpler because all the y's would be treated as constants. If you had to integrate with respect to y first, right, then you've got y's in multiple places. And when you integrate with functions that have variables in multiple places, that's typically integration by parts. So this would turn into an integration by parts problem if we tried to integrate with respect to y first. So it would be better to do x first. All right, and then if you're going to do that, then you'll have y squared e to the xy, and we're going to have dx dy. All right, so if we're doing dx dy, then that means we've got x bounds for the inner bounds, y for the outer. So effectively, this means we're going to be using type 2. We're going to be using the blue rectangle, not the red. If we're using the blue rectangle, right, then what does that mean? So that means the bottom bound is the left side. The left side is at x equals 0. All right, and then the top bound is the right side. The right side is at x equals y, right? We wrote y equals x, but also x equals y. And then we want to do that from y equals, right, the bottom is at y equals 0, and the top is at y equals 4. Okay, and so that's how you go through and set up the order of integration when it's not specified and you have an object, you have this object, is we have to go through and choose, and we're going to choose type 2 because the order of integration would be easier. All right, so now that we've done that, we can go through and actually evaluate the integral. So the antiderivative of e to the xy here. So this is a u substitution. Let's actually write out the substitution. So we're going to have u equals xy, and then du. So if we're integrating with respect to x, then that means we're going to differentiate with respect to x, and so we're going to have y dx. Okay. So if we do that, we've got 0 to 4. Now we need to change the bounds on this 0 to y. So you're going to take 0, plug it in for x, and so that's going to be at u equals, so it's going to give us u equals 0. And you can write that if you want. You can write u equals 0. These outer bounds are still in terms of y. And then you're going to take x equals y, plug it in, and so we're going to get u equals y squared. Right, if we could take that and plug it in. Okay, and then our inner piece here. So we're going to have, let's see, what are we going to have here? So we need y dx to go through and have our du. So we've got y squared dx. So that means we've got an extra y there. So you could think about, you could just peel off one of those y's. So we'll write that first. That's y to the first, right? And then after that, we'll have e to the u, and then du. And again, so du has y dx. That's where the other y went. So there's one y here, and then the other y dx is buried inside of the du. All right, and then when we've done with that, we've got dy, and then we can go through and do, now we're integrating with respect to u here. So the antiderivative e to the u du is going to be e to the u du. Just ignore the y. Sorry, the antiderivative e to the u du is just e to the u. So 0 y squared dy. Take that and plug it in. So when we plug in y squared, we'll have y e to the y squared. Plug in 0, you'll get 1. Those nasty ones are so easy to forget. I was looking at my notes and I forgot that one. They are so easy to forget. All right, so we plugged in y squared for u. We plugged in 0 for u. We got that. All right, so I might actually go to another page here. So to go through and evaluate this integral, we've got 0 to 4. This is y e to the y squared minus y dy. Okay, maybe I'm just going to cheat here, right? So the antiderivative of e to the y squared y is going to be, that's going to be 1/2 e to the y squared. Okay, so the way that you could tell here is, the nice thing about finding antiderivatives is you can always just differentiate to check them. This one's a pretty easy one to check. The derivative of e to the y squared is going to be e to the y squared times 2y. And if you take the 2y and multiply by 1/2, you're going to get y e to the y squared. So this is one that you could kind of guess and check your way through. And then the antiderivative of y would be y squared over 2. And then 0 and 4. So we're going to get 1/2 e to the 16 minus, right, 16 over 2. That's going to be 8 minus, plug in 0. If you plug in 0, we're going to get e to the 0. That's going to be 1. So we're still going to have that 1/2 there, though. So we have minus 1/2. And then 0 here is just going to give us 0. All right. And so this is 1/2 e to the 16th. And then minus, what are we going to get here? So this is going to be minus 8 minus 1/2. So that's minus 16 halves minus 17 halves. Hopefully that's correct, because my notes don't have the minus. I forgot the -1 in my notes. So anyway, hopefully we got that. All right. Let's move on to the next example. So what we're going to do now, so we've gone through and we've done a couple problems where they gave us the integral and they asked us to go through and set it up. All right, so the next thing that we're going to do is, what if they didn't even give us the integral? What if they asked us to find the volume of a solid and then they describe the solid? Okay, so if you're asked to go through and find the volume of the solid and you're just given a description of the solid, then what you need to do at minimum, you need to sketch the base of the solid. Okay, depending upon the instructions and the object itself, it may be helpful to sketch the solid. So I will show you examples and we'll discuss that in more depth. Some instructors bend over backwards to try and avoid sketching the solid. And I think that's because some students have a real hard time sketching the solid. I kind of take the opposite perspective. I think that it's worth really building up your skills at sketching solids, um, because I think that it makes it a lot easier if you can sketch the solid. And so trying to dodge it in the end is just going to kind of be counterproductive. But I will try and show you both ways. So if you really, really, really do not want to sketch the solid, I will try and show you how I think you could do it without sketching the solid. But that's not really my forte. I usually go ahead and sketch the solid when I need to. So you're going to determine whether the base of the object is type 1 or type 2 or both. So sometimes it will be both. And if it's both, then that means that you have a choice in your order of integration. Once you've done that, you're going to set up the integral. All right, so this time I'm just going to go ahead and write the integral for you. So your integral should look something like this. You're going to set up the integral. Then the top of the object, the top of the solid, I mean, the top vertically, right, is z equals f of xy. Okay. And then the order of integration and the inner bounds, right, and the bounds are based upon whether the object is type 1, type 2, or if both, you have a choice. Or if both, you have a choice. Okay, so these problems become increasingly more difficult as you progress. So let's see if we can go through and do some of these problems. See if we can successfully do them. All right. So what might you be asked to do? You might be asked to go through and find the volume under the surface z equals 1 plus xy and above the region y equals x squared. Oh, sorry, the region enclosed by y equals x squared and x equals 4. Okay, so one of the things when you're doing these problems that's important to try and recognize right off the bat is how does the surface interact with the region, or do they interact? And so in this problem, it says find the volume under the surface and above the region. It's implied in terms of those instructions that the surface itself is not interacting with the region. That will not always be true, right? So just to give you an idea of a different set of instructions, like what if the problem had said, find the volume bounded by z equals 1 plus xy, y equals x squared, and x equals 4. So if it just says that the solid is just bounded by a bunch of things, then the top of the object could also end up forming, end up creating parts of the, the limitations on the sides. Okay, and I'll show you what I mean by that in a later example. But if you imagine a three-dimensional object, the sides and the top interact with each other. So if you're just told that it's bounded by a bunch of things, those are the hardest problems to do. The problem is specific. You've got something that's under a surface and above a region. So it's basically the problem has separated the two for you. All right, so you've got this is one piece. This is the top. So you're told specifically that's the top. And then you're told specifically this is the base, right? If you read it carefully, the two are broken into pieces. And that makes the problem easier. So that's why this is the first example we did, is because of that. All right, so it is important that you be able to identify, the differences, these subtle differences between the problems, so that you know exactly what you need to do. So because of that, we don't need to think about the top at all, except for when we're actually doing the integration. We can just focus on the base, which is the most important part of doing these problems, is determining whether it's type 1 or type 2. So let's go through and sketch the base. Right, so it's the region enclosed by y equals x squared That was terrible. It is so hard to draw with this stupid writing tablet. Y equals x squared, and then x equals, oh, x equals 4. Oh, oh, I made a mistake. My apologies. It's supposed to be x equals y squared. Yeah, that didn't make any sense the way that I had it. All right, so let's, it's easy to fix. So let's go through and just reverse these, right? So if it's x equals y squared, then it looks like this. Oh, geez, I give up. All right, and then x equals 4. All right, so there's our object, the region enclosed by x equals y squared, and x equals 4. And so what we want to do is look at this. Is this type 1 or is it type 2? Well, it could be both if you really needed it to. I would say that the easier way to do this one would be as a type 1, type 2, based upon what they gave you, right? So the giveaway, we discussed this earlier. The giveaway is if they give you functions of y, I guess there's no function of y here, but if they give you x equals, x equals things are functions of y. And so that's going to be left to right. However, this problem would not be that difficult to go through and solve for and create a consistent top and a consistent bottom, you know, by going through and solving for y here. So you could, if you absolutely needed to, if it was absolutely critical, you could go through and do y equals plus or minus root x, and then this would be positive root x, and this would be negative root x, and then you'd have a consistent top and a consistent bottom. However, I wouldn't do that unless you need to, because clearly they're giving you some instruction here. They're giving you x equals and x equals, so it's implied that you're supposed to use this, supposed to do this problem as a type 2. All right, so once we've looked at all that and thought about all that, we want to set up our integral, our double integral. We want to take the top of the object. That goes here. Okay, we've identified type 2. So type 2 is dx dy, right? That means the inner bounds are x equals, outer bounds y equals, and y equals. All right, so the x equals, so we're going from left to right. So the left is given by x equals y squared. The right is given by x equals 4. And then for the outer y bounds, we actually don't know what those are. We need to know what the bottom and the top are. So how could we find those? How could we find those y bounds? Well, what we could do is we could go ahead and we have x is y squared and x is 4. We've got two functions here. If you set those equal, we could go through and create an equation that just had y's in it, right? So you'd end up with 4 equals y squared, and then plus or minus 2 equals y. So we would do from -2 to +2. Okay, so this video is getting really long. I don't time them, but I'm guessing we're probably hour and change, hour and a half mark. So this is what I got going through and doing all the steps. Hopefully it's correct. So 160 thirds. So you can go ahead and check that and see if I got the answer right or not. And you know, if not, you can say something in the comments. All right. Let's move on to the next problem. Find the volume of the solid enclosed by the paraboloid z equals x squared plus y squared plus 1, and the planes x equals 0, y equals 0, z equals 0, and x plus y equals 2. Okay, so now we have our first really good example where you could think about sketching this. You could think about sketching the solid, or you could think about just trying to sketch the base of the solid. You have some choice here. All right, why is that? So if you read the problem, find the volume of the solid enclosed by a bunch of different things. Well, the paraboloid here could end up making part of the base, depending upon the way that the planes are set up. So it could be if you had the right paraboloid, then the right paraboloid might restrict what the region that you're, what the base of the region is going to be. That doesn't turn out to be the case in this problem, but we're going to do one more, and I intentionally picked one where that was the case so that you could see what they look like. All right, so what I would do if I were doing this problem, I would go ahead and just sketch the object, because this is not a difficult object to sketch. But I'll try and explain how to do it if you're not going to sketch it. All right, so if you go ahead and sketch the object, what do we have? Well, we have the paraboloid z equals x squared plus y squared plus 1. So if you think of the base paraboloid z equals x squared plus y squared, this is effectively that bowl shape, but shifted up 1. So if you just go to 1 and then draw the, the upward shaped paraboloid, oops, geez. Even that line's not great. Anyway, so here's the paraboloid. So it doesn't take terribly long to go through and draw the paraboloid. If you don't recognize that this is the base paraboloid shifted up 1, then it's going to take longer if you're going to go through and use cross sections to figure out what it looks like. You have to set x equal to 0 and y equals 0 and z equals 0. You got to set a bunch of things equal to 0. But you could still do it. It just would take a little bit longer. All right, so we've got our paraboloid. It looks like that. What is x equals 0? X equals 0 is the y-axis. Right, so that's there. I don't know, you could try and do something to remind yourself of that. Right, so we've got x equals 0 is the y-axis. Y equals 0 is the x-axis. We have z equals 0, so we have the xy plane. What did I say? Did I say y-axis? X equals 0 is the yz plane. Y equals 0 is the xz plane. I don't know why I said that. All right, and then finally, x plus y equals 2. So x plus y equals 2, you've got to remember all these details, but x plus y equals 2 is a cylinder because there's no z coordinate. And so to go through and sketch a cylinder, what we could do is we could go through and just graph x plus y equals 2 on the xy plane and then just shift it upward to do the cylinder part. All right, so what does x plus y equals 2 look like on the xy plane? Probably the easiest way to do this is to plug in 0 for x or y and then solve for the intercepts. So if you set x equal to 0, you get y equals 2. So that tells us that y equals 2 lies on the plane x plus y equals 2. And then if you set y equal to 0, you get x equals 2. So we get x equals 2. That lies on the plane x plus y equals 2. And so if you just connect those, that is x plus y equals 2 drawn on the xy plane. And now if you just extend that upward, what happens? You extend it upward until you hit the object. It hits the object here, hits the object here, and you kind of get this type of a shape. That is our object. And that's all that it takes to go through and graph it, is to draw the paraboloid, note the planes that are forming the sides. So if you were to mess up your picture like I'm about to, right? The y equals 0, that tells you that this is the left side. The x equals 0, that tells you that this is the back. Now, I'm not going to sketch it because it would truly destroy the picture entirely, but you could think of it like the front is defined by this plane here that's shifted upward, and then the top is the paraboloid. Okay, so now using this picture, what you can do is you can go through and you can just very easily sketch the base. So what's the base in this picture? Like what's the bottom? Like what's the bottom of the object? Well, it's just this triangle here. All right, so you get this triangle here at the bottom. That's the base, and so it went from 2 to 2, and this was x plus y equals 2. So this is the important part, right? So this is what you have to be able to do. This is optional. So you can see once you have this picture, going through and figuring out that the base of the object is this triangle that's directly beneath our surface and bounded by these equations is really easy to do. What if you didn't have the picture? How could you go through and come up with this? How could you go through and come up with the base if you wanted to avoid graphing it? Okay, so if you're going to do that, that's not how I do it, but I think that's but some people like do it like some instructors do it that way, and so clearly it's possible. What you need to do is you need to check, does the top of the object, does the surface that you're finding the volume beneath, does the surface intersect the bottom of the object, right? And so if you're going through and looking at this, z equals 0 is the bottom of the object, z equals x squared plus y squared plus 1 is the top of the object. So what you need to do is you need to take z equals 0 and plug it in and see if you get any solutions, right? So if you try that, what happens if you take z equals 0, plug it in, right? We get, if you try this, so this is what you'd have to do. You're going to have to do 0 equals x squared plus y squared plus 1. And so that turns into x squared plus y squared equals -1. And there is no solution to that. So that is good news, because if this is the bottom, that's saying that the top never intersects the bottom. If the top never intersects the bottom, then that means that you don't have to worry about the top forming part of the base. All right, so once you've checked that, you can just put a little note for yourself, not part of the base. At that point, you can kind of ignore it in the same way that we ignored the top here when it came to finding the base. Once you've determined that the top is not part of the base, now you can just focus on these equations here. What do they say? X equals 0. X equals 0. That's the y-axis. Y equals 0. That's the x-axis. Oops. And then finally x plus y equals 2. That's this line. And so you end up getting here, here, and here. So that's how you could do it without sketching the solid, right? So if we just pretend the solid was not there, first you check, does the top intersect the bottom? If not, ignore it. Once you're ignoring it, then just focus on the rest. And so this ends up forming the base once we have eliminated the possibility that the top is part of the base, right? And then so to go through and set up the integral from there, right? We have our double integral, put the top in there. That's going to be x squared plus y squared plus 1. Order of integration. Oh, take a look at our object. We still need to figure that out. Is it type 1 or type 2? I would. It's both, right? And order of integration, it doesn't matter, right? This could be easily integrated with respect to x first or y first. What I tell students, if you have a choice, if it's both, and the order doesn't matter, then usually it's easier to do type 1. That's kind of the default. That becomes the default. So for type 1, that means we want functions of x. To turn this into a function of x, we do y equals -x plus 2. And then we can then, hold on. I intentionally left it unspecified so that I could fill it in. All right, so if we're doing type 1 here, that would be dy dx, and that means we have y equals to y equals and x equals to x equals. All right, so what's our y equals going to be? So when we're doing type 1, it goes from the bottom of the base to the top of the base. So that's going to be from y equals 0 is the bottom of the base to y equals negative x plus 2 is the top of the base. And then we go from x equals the left side, that's going to be x equals 0, right? X equals 0. And we go until we want to stop. And it looks like we stop at x equals 2. Okay, these ended up kind of on top of each other. Let's just, we've got x equals 0 and then y equals 0. All right, and that's your integral. Okay, and so from there, you go ahead and set up, you go ahead and evaluate it, right? Integrate with respect to y, plug in 0, plug in negative x plus 2, integrate with respect to x, plug in 0, plug in 2. Now, assuming I did that one correctly, you should get 14/3. Okay. And yeah, I'm not going to go through and do the integral again just for time, because I think this video is getting way too long. All right, let's go through and do another one. Let's do one where, I keep bringing this up, let's do one where the top of the object ends up forming part of the base, because those are going to be the hardest ones. Those are going to be the ones where you're going to really need to know what you're doing. All right, so let's say you're told to go through and find the volume of the solid bounded by the cylinder y squared plus z squared equals 4, and the planes x equals 2y, x equals 0, z equals 0, and where all of that is in the first octant. So first octant, I don't think that's come up yet in any videos so far. The first octant is where x, y, and z are all positive. Okay, so it's kind of like quadrants, when it comes to, going through and defining 2 dimensions. But, but it's in terms of there's 8 different octants that would surround the origin for in 3-dimensional space. And the only one that's numbered is the first octant. I've never heard any definition for where the 2nd, 3rd, 4th, 5th, 6th, 7th, or 8th octant is. So you usually only hear about the first octant, but the first octant is where x, y, and z are all positive. Okay, so I'm going to do this. I'm going to do this problem in the reverse order that I did the last one, because I think once you see the object, it's easy to figure out what the base would be. And so normally I would go through and sketch the object, and if I could, and in this case it's easy to sketch. A cylinder this is an easy cylinder to draw. These are easy planes to draw. So it's easy to go through and figure out what the object looks like. But some students don't want to do that. They don't like graphing solids. And so how could you do this problem without graphing the solid? So I'm going to do that first, and then I'll graph the solid second, and basically show you how I would have done it initially. All right, so you hate graphing solids. How can you do this? All right, so what you need to do is you need to be able to look at the information they've given you and identify some stuff, right? So you've got the volume. It's bounded by the cylinder, y squared plus z squared equals 4. So if that just looks like a bunch of symbols, that's a little bit of a problem. You need to be able to know that the cylinder, it's got a z in it, right? So as soon as you see a z in it, that means that it could form the top of the object. All right. Now, if you keep reading, you've got z equals 0 and y squared plus z squared equals 4. Those are 2 z related things. So one forms the top and one forms the bottom. That's the way that you've got to think about it. And what you could do to try and maybe figure that out, and this is again, this is your goal is to graph nothing. If you solve for z, you're going to get z equals plus or minus the square root of 4 minus y squared, right? If you solve for it, and so this plus, that tells you that there's part of the part of the cylinder is above the, has a positive z value, so it's above the xy plane, and part of it's below, so it's below, right? So you have, below the xy plane, and so you do have part of the object here is above, and then if you combine it with z equals 0 and the first octant, you can try and puzzle out without doing any drawing that this is that the positive here is the top, and the z equals 0 is the bottom of the object. Okay, so you do have to kind of do some finagling to identify those two. Once you've figured out that this is the top and this is the bottom, your next step needs to be, does my top intersect with my bottom? If it does, then that could form part of the base. So how do you figure that out? Well, you can just take z equals 0 and plug it in. Just plug it in, and that will tell you. All right, so if you plug in z equals 0, what happens? You're going to go from y squared plus z squared equals 4. You're going to go to y squared plus 0 squared equals 4, or y equals plus or minus 2. So what the top of the object here did intersect the bottom of the object. It intersected at plus or minus 2. Now, again, because of the first octant part, we don't care about the negative. We only care about the positive. So it intersected at y equals 2. So what you need to do is you need to graph y equals 2. You say, well, there's no y equals 2 here. Yes, that's exactly the point. That's what makes this a hard problem, is that y equals 2 comes out of nowhere. That forms part of the base. It's the part of the base where the top intersected the bottom of the object. Okay, and then so once you've got that, then you can go through and graph x equals 2y. That's the same thing as y equals 1/2 x. So y equals 1/2 x, you go up 1 over to, we'll say that's there. And so y equals x equals 2y, you're going to get that line. And then finally, you're told x equals 0. What's x equals 0? That's the y-axis. And so this is the base. Look, so we figured out what the base is without graphing the object at all. Okay, but that's, you've got to do something like that. You've got to determine what the top is. You've got to determine what the bottom is. You've got to figure out, does the top intersect the bottom? If it does, then you need to go through and graph that, and then you can combine it with the rest. That is not how I would go through and do the problem, though. But that might be the best way that works for you. So that's okay. That's okay. You don't have to do it the same way that I do it. But let me go through and show you the way that I would do it. We're going to end up doing parts of this stuff again, but it's just the picture of the object contextualizes everything, and in my opinion, just makes it a much simpler problem. So you go through, you've got your 3 dimensions. All right. Y squared plus z squared equals 4. So you need to be able to recognize that's a cylinder. It's a cylinder that's been shifted in the x direction. So if we're going to go through and graph it, the way that I described earlier videos, you want to go ahead and graph the circle, y squared plus z squared equals 4 on the yz plane, and then extend it in the x direction. All right, so we're going to say that's 2, -2, 2, right? And the -2 is down there below. We actually don't care about the bottom because of the whole first octant part. So you go through and you graph the circle. Geez. All right, that's gonna have to be as good as it gets. Now we're gonna take it, then we're gonna extend it in the x direction to go through and sketch it. Can't seem to get that right side correct. All right, when we do that, we're going to go ahead and put lines on there to represent the shifted part. So we've got line, a line. Actually, we don't even care about the left-hand side. I don't know why I'm drawing the left-hand side, but just for completeness. So there's the cylinder. All right. And then we have the plane. So z equals 0. That's the xy plane. So that's below the object. And then we have x equals 2y. So x equals 2y is just a line that's going through the origin, okay, with a, with a 1/2 slope, right? So the way that you could go through and graph that is, it goes through the origin. Oh, by the way, this is also a cylinder because it doesn't have a z coordinate. So we're going to graph it on the xy plane and then extend it in the z direction. So what you could do is it goes to the origin, and then because of this other line here, you could figure out, well, where does it equal 2 for y? So if you plug in 2 for y, it equals it at 4 for x. So we're going to get this point 4 comma 2, all right? And then you could go through and sketch that, extend it in the z direction. This would be the top of it. As it extends in the z direction, it's going to cut through our cylinder. Where does it cut through our cylinder? Well, to figure it out, you've got this point is going to be part of the plane. This point is part of the plane, and so all you've got to do is just draw a curve that looks like that. There's your object, and the base of the object is the part that's directly here at the bottom. And what can you see by looking at the base of the object? You can see that if we're going to go through and now sketch the base, what is the base? The base is determined by, you've got y equals 2. Right? And then we have x equals y squared. And then x equals 0. So if you are capable of going through and graphing the object, then this picture just kind of jumps off the page at you. But that's very difficult. That can be difficult for some people. So if you want to go through and do it that first way, you could try it that way. As far as setting up the integral itself, so we need to have the function. So what is the function, right? To have the function, you need to have the top. Well, you can clearly see from our picture, or you can recall from earlier that we figured out what the top was by solving this for z. So we get z equals, it's going to be plus or minus, but we don't care about the minus. So it's just going to be z equals 4 minus y squared. So we're going to have the square root 4 minus y squared dA d. All right, so there's our integral. So I'm compartmentalizing it this time by just doing it in 2 steps. So first, just plug in the function, and then we're going to figure out the order of integration. What should the order of integration be? Well, if you look at this object, is this object type 1 or is it type 2? It's both. All right, so you could go through and have a rectangle that goes this way, or we could have a rectangle that goes this way. They both work. We've got a consistent left and a consistent right. You've got a consistent top and a consistent bottom. And so you have a choice. So when you have a choice, what do? You look to the function. Which would you rather integrate with respect to first? Would you rather integrate with respect to x here, or would you rather integrate with respect to y? Now, you don't see any x's, right? So if you integrated with respect to x, this whole thing is just going to be a big constant, and then it would be really easy to find our antiderivative because this is going to be the antiderivative dx. If we integrate with respect to y first, then x would be treated as a constant. There's no x's, so who cares? But we'd have to go through and integrate this with respect to y. Now, it may have been a bit, but if you're going to integrate the square root of 4 minus y squared with respect to y, that's a trig substitution. So you'd have to go back and check your notes, or hopefully maybe you remember how to go through and do a trig substitution. But me personally, I do not want to go through and do a trig substitution if I don't have to. So I'm going to integrate with respect to x first. And the reason that you do that is you just hope that the trig substitution goes away if you do that. I kind of discussed that a little bit in the previous video. All right, so if we do x first, then what are the x bounds? So we want to go, when it comes to x, if you're doing x first, it goes left to right and then bottom to top. So the left here is at x equals 0. The right is at x equals 2y. And look at that, they even set it up for you. They're kind of telling you, hey, you should do this type 2, left to right. And then y, we go from 0 to y equals 2. Okay, and so I'm not going to do the whole integral here, but I do want to just show you how easy this is if you do it in this order. So the antiderivative of root 4 minus y squared dx, the root 4 minus y squared is all a constant, so just ignore it. The antiderivative dx is x, and so you get 0 to 2y dy. And then if you do that, we'll have the integral 0 to 2, plug in 2y, and so you're going to have 2y root 4 minus y squared. Okay, and then you plug in 0 and you get 0 dy. And now this, maybe not a blast to do, but it's just a u substitution. You can go through and set u equal to 4 minus y squared. And then du equals negative 2y dy. And so you can put the negative here, and then this becomes the integral, plug in 0 for y, and you're going to get from u equals 4, plug in 2 to u equals 0, and then this is going to be the square root of u, right? That's u, and then negative 2y dy is du, so it's root u du, and from there it's a very short, easy integral. You should get 16/3, assuming I did not make any mistakes. Okay, and so that concludes the video. Thank you for watching. See you next time.